In this video, we're going to look at how we find the equation of the inverse function. So in our last lesson, we explored different ways in which we can graph the inverse function. We looked at the inverse as a reflection about the line y equals x, so that's just this line over here. So it's kind of like a reflection along that diagonal. And we said that the way that we sketch the inverse graph is if we take any coordinate x comma y, and we know that that would map onto y comma x. We notate the inverse function as f to the negative 1 of x. So this actually gives us a clue as to how we can find the equation of the inverse function. If x comma y, if all points x comma y map onto y comma x, then really the way to find the inverse function is just to swap x and y. Now you're going to see that if y doesn't exist, if the question was given to us just in the terms of f of x equals some rule, we're going to need to notate a few things just so we can create a coherent mathematical argument. But ultimately, we can think of finding the inverse as swapping x and y. Sorry about that, the screen just jolted, but swapping x and y is our first step. Our second step would be to solve for y. So if I had a rule y equals something something and I swap them, I'd need to undo that something something in order to isolate y. So swap x and y, solve for y, and ultimately we're going to give our answer in terms of the inverse equals. Now another interesting property that we're going to look at is the fact that when we do find the inverse function, the domain of that function is the old range of the original. So the domain of the inverse is the range of the original. Vice versa is true as well, that the range of the inverse is the domain of the original. So this can come in quite handy when we're asked to state the inverse function, state its domain and its range. So quite simply, that can be summarized as the fact that the rule of the inverse can be obtained by swapping x and y and making y the subject. One other important distinction to note is that only one-to-one functions can have an inverse. And we're going to see what that looks like in a moment. So in this example, we're asked to find the inverse. Okay, so the thing that we're trying to find is the inverse function of f of x equals the square root of 2x plus 1. We're also asked to state the domain and the range. And so the context here that isn't actually given is what we need to know. The domain of the inverse is equal to the range of f. And vice versa, the range of the inverse is equal to the domain of f. Now, it's all well and good to say swap x and y, but in this question itself, there really is no y. It wouldn't make sense to suddenly introduce y. And so what we need to do is we need to state the function f is such that y equals f of x. So it's kind of like saying let y equal f of x. And if that's the case, then the inverse function would be such that x equals f of y. This is how mathematically we write the phrase we're swapping x and y. And so for the inverse, we know that x is equal to the square root of 2y plus 1. So all I've done there is I imagine that that was a y, and then I swapped it with the x. So that's really all we're doing. We're swapping x and y. In order to solve for y, we need to square both sides. And for me to start doing this solving for y, I would rather work left to right. So I'm going to swap this around and say the square root of 2y plus 1 is equal to x. If we square both sides, 2y plus 1 is equal to x squared. If we subtract 1 from both sides, that yields 2y is equal to x squared minus 1. And finally, y is equal to x squared minus 1 on 2. Now, I was asked to find the inverse. So to make sure that I haven't just introduced this variable y and forgotten what I was actually doing, I need to demonstrate to the examiner the inverse of x is equal to x squared minus 1. I want to demonstrate to the examiner that I know what I found. So given this is the inverse, we now address the second part of the question. We want to state the domain and range of the inverse. To do that, I think it's always best just to examine this square root of 2x plus 1. Examine the f of x first. Just at a quick sketch, I think, okay, this is a square root function. So what's under the square root? That 2x plus 1, well, that can't be negative. So I'm going to let that be greater than or equal to 0. So 2x is greater than or equal to negative 1, and x is greater than or equal to negative a half. Our endpoint in this case is negative 1/2. So how do I use that information in order to find the domain and range of the inverse? Well, I know that the range of the inverse, ran f, is equal to, that's ran f negative 1, the range of the inverse, is equal to the old domain, which we said was greater than or equal to negative a half. So my new range will be negative 1/2 to infinity. Now the domain of this inverse, well, that's the range of the old function. And looking at this, it starts at negative 1/2, 0, and then it just goes up. So all the possible y values there are from 0 to infinity. So my new domain, being the old range, is 0 to infinity. So there you have it. We've found the inverse of the function. We've also stated its domain and range. Looking at our next example, I'd like you to pause the video here and give this one a go. So I'm going to give you a little bit of time to try it and see what we get to. So hopefully you've given it a go, and I'm guessing that you may have encountered some trouble. And it's exactly why I've put this problem here. It's a very common one. And actually the question is quite poor. Because x squared plus 8x, if we think, well, what is this thing? What is this g of x? If I sketch that graph and I took x out as a common factor, I'd have x outside of x plus 8. So that's a quadratic that passes through the origin, passes through negative 8, and looks like this. So this thing is not 1 to 1. And so the inverse function actually doesn't exist. The answer to find the inverse of g of x equals x squared plus 8x is that the inverse doesn't exist. But let's change the question now. Let's say that instead of that being the case, we're going to say g of x is equal to x squared plus 8x, and that x is greater than or equal to negative 4. So what we're doing here is we're restricting this graph at negative 4. So we're restricting it at the turning point, which does make the quadratic 1 to 1. Now I can go about this as usual. I don't have the function f, I have the function g. So I'll say g is such that y equals g of x. To swap x and y, the inverse of g is such that x equals g of y. And so y squared plus 8y is equal to x. This is what I'm solving for the inverse. If you did try this on your own, I'm guessing you may have had some trouble trying to get y on its own because there are two y variables here. What we need to do in this case is complete the square. So if I imagine that I've got this a equals to 1, the coefficient of y squared, and b is equal to 8, the coefficient of y, c is equal to 0 because there is no constant term, I can complete the square by using the formula x minus b on 2 squared, or plus b on 2 squared I mean to say, minus b squared on 4 plus c. And so if I use these variables, y plus b on 2, which is 4 squared, minus b squared on 4. Well, 8 squared is 64 on 4 plus 0 means that I get the equation y plus 4 squared minus 16 is equal to x. This is now something I can solve for y. So adding 16 to both sides, y plus 4 squared is equal to x plus 16. If I square root both sides, y plus 4 is plus or minus the square root of x plus 16, and y is equal to negative 4 plus or minus the square root of x plus 16. Now our question is it plus or is it minus? It can't be both because it must be a one-to-one function. And if it was both, we really have a relation and not a function. So how do we determine this? Well, if I imagine my graph x squared plus 8x, and I know that the domain is negative 4 to infinity, then it turns out that for my inverse function of g, negative 4, now we're going to do plus or minus the square root of x plus 16. Let me just rewrite that so it fits on screen. So inverse of x is negative 4 plus or minus the square root of x plus 16. I know that the range of the inverse must be negative 4 to infinity. Negative 4 to infinity. So that means the lowest value I can have is negative 4, and I can only add something to that. I can only add value. It has to get bigger. So I can't subtract the square root, which of course is always positive. So that tells me that I had to use plus and not minus. Now the domain, while I could read it as the range of g, it's easier here to see that the domain will be negative 16 to infinity. So I can choose to read that from inverse g. So the domain of inverse g is negative 16 to infinity. As a general rule of thumb, because I know that a lot of people find it far easier to find the domain than the range, you could kind of solve these problems only ever using the domain. If I know the domain of g, then that's the range of g inverse. If I have the rule of g inverse, I just need to find its domain. Now our final example for the video is one that's a little bit more tricky, and this is something that's far more common of an exam question. We're asked to consider the function f such that reals map onto reals. So remember, this onto real, that doesn't matter, that just says we're working in the real field. The output could be a real number. But what does matter is that the domain of f is equal to reals. And we're told that f of x is x outside of x minus 4. So we've got a quadratic that passes through 0 and 4, so it's going to look something like this. So it's just going to be y equals f. Now we're also told that g, so the domain of g, is equal to 3 over 2, 5. Okay. So g is equal to 3 over 2 to 5. And g is just a linear line x plus 3. So that's just going to be a straight line x plus 3. If the function h is equal to f plus g, so let's try and define that function h. We say, okay, that's going to be f, x outside of x minus 4, plus g, which is x plus 3. Then the domain of h inverse is, so now we actually get to the question stem. The question stem is, what is the domain of inverse h? Well, let's have a closer look at h. If I expand that out, I know h of x is equal to x squared minus 4x plus 1x plus 3. And so we get x squared minus 3x plus 3. But what you may not know is that if we are adding f plus g, then we can only add functions over a shared domain. So the domain of f, if I imagine a number line here, well, f was just, let's do that in blue, that was just reals. But the domain of g was from 1.5, so let's call that 3/2, to an exclusive 5. Now what's the shared domain? What's the overlap? And of course the overlap is just going to be g. So not only is my function for h x squared minus 3x plus 3, not only is it that quadratic, but also x is an element of 3/2 to 5. Now, why is this useful? Well, I need to find the range of h. I know that h is a positive quadratic, so let's go some background information here. H is going to look like, I don't know where it's going to hit the axes, but it's going to look like a positive quadratic. And the range of h is from the turning point to its end point. Now normally that might be to infinity, but we've got to give an end point. So how do I find the turning point of h? Well, remember that the axis of symmetry is negative b on 2a, which is negative 3, so positive 3, on 2a, on 2. Well, that happens to be our endpoints. That's a really, really handy thing to have, because h of 3/2 is equal to 9/4 minus 9/2 plus 3, which I might write as 12/4. And 9/2 I might write as 18/4. And so 9 plus 12, so that's going to give me 21, minus 18, it's going to leave me with 3/4. So I'm going to move the screen over a little bit to give me just a tad more room. So I know that the lowest point on this graph is 3/4. That is to say, the range of h rather. So the range of h is equal to 3/4. Now the highest point will be to the right of the turning point at an end point that is 5. So I think, well, what is h of 5? Well, I've got 5 squared, so that's 25, minus 3 times 5, minus 15, plus 3. That gives me 10 plus 3, which is 13. So the range of h is 3/4 to 13, not including the 13. The reason that I did all of that is to state that the domain, that's what we're after, the domain of h inverse. The domain of h inverse is therefore 3/4 to 13. So this can be quite a tricky question because, one, we need to know a thing or two about the function h, about the addition of ordinates, about the fact that when we're adding graphs, we can only use the shared domain. 2, some people will do this by finding the inverse and trying to imply its domain. Now, finding the inverse of something like this can actually be tricky. You'd have to complete the square, which a lot of people will have some trouble doing, but also it's a lot of unnecessary work. Ultimately, what you may end up with is a domain where you can see the minimum value is 3/4, but you may not know that maximum value occurs where x is 5. So in h, excuse me. So it occurs where y is 5. So it's really important that we have this deeper understanding of domains and ranges. This is certainly a challenging question, but if you could work your way up to this by the end of the year, you'd be ready for the exam. So in summary for today, we know that we can find the rule of the inverse by swapping x and y and making y the subject. The way that we write this is to say f is such that y is equal to f of x. The inverse function is such that x equals f of y. So that's how we literally say swap x and y. We need to make y the subject. and then replace it with inverse of x. It's important to note that only one-to-one functions have an inverse. And so careful adherence to reading for the domain or looking at a given range is going to be really, really important. Something else to note, which we looked at in detail in the last video, is that the inverse of x, when we let it equal f of x, so when we let one function equal its inverse, that'll always occur on the line y equals x. And so finding that point of intersection is as simple as letting one or the other equal x.